Good morning, students. Today we will study about the negative deviations from the ideal solution behavior. Okay. Yesterday what we have read. Yesterday we have read about the positive deviation from the ideal behavior. Today we will read about the negative deviations from the ideal behavior. Okay. Positive. Why the solutions undergo positive deviations? Because there is the uh, there is the force of attraction between the solute and the solvent molecules will be less. That's why it undergoes what? It undergoes positive deviation. But here we have what? No, we have what is the important factor is that the force of attraction between the solute and the solvent particle is greater than the solid particles and the solvent particles. So what are the necessary conditions for the negative deviations from the ideal behavior? The necessary conditions for the negative deviation from the ideal behavior is if FAB is greater than FAA and FBB, where A is the solute and BB is the solvent. Here, by showing this, what we are trying to say that the force of attraction between the solute and the solvent molecule is greater. The force of attraction between the solute and the solvent molecule is greater than the force of attraction between two solute molecules and force of attraction between two solvent molecules. It means the solution formed by mixing of the solute and solvent has the greater force of attraction between themselves. Okay, understood? Due to this, they undergo negative deviation. Now, we are going to show this by using a graph, by using a one diagram. Here, XA is equal to 1 and XB is equal to 0. Okay. XA is equal to 1 and XB is equal to 0. XA here is the mole fraction of A and XB is the mole fraction of B. Here XA is equal to 0 and XB is equal to 1. Okay. Here what? P naught A, pressure of the solute at its pure form. Okay. And here P naught B, pressure of the solvent at its pure form. P naught B, what is P naught B? Pressure of the solvent in its pure form. Okay, this diagram is like this. What is the total vapor pressure of the solution? The total vapor pressure of the solution of the ideal gas is drawn like this. This is the graph for the ideal solution. This is the diagram for the ideal solution. But when the solution is not the ideal solution, there is deviation. There is some kind of deviation. In the present case, it is negative deviation due to the higher force of attraction between the solute and the solvent molecule. What happens? It means there is a negative deviation. So this graph goes like this, downward curve. This graph goes like this and this graph goes like this, the downward curve. It is a downward curve. Understood? By this graph, we show the negative deviation of the solution from its ideal behavior. Okay, this graph shows the negative deviation of the solution from its ideal behavior. This deviation is due to the greater force of attraction between the solute and the solvent molecules. Understood? Now, why there is the negative deviation is taking place? Negative deviation is taking place because of the greater force of attraction between the solute and the solvent molecules. Now, after making the solution, solute and solvent molecules are not able to vaporize in the more quantity as it vaporizes earlier. Okay, we have the solution, which has the greater force of attraction between the solute and the solvent molecules. Now, less number of moles of the solution vaporizes in the container, and if the less number of solution particles vaporizes in the solution vaporizes in the container, it exerts less vapor pressure. That's why there is negative deviation from the ideal solution. Understood why there is a negative deviation? Because due to the greater force of attraction between the solute and the solvent molecules, less number of moles of the solution get vaporizes, and it exerts, as a result of which it exerts less number of vapor pressure on the solution surface. Understood? So what are the another conditions for it? The another conditions for it, along with FAB is greater than FA and FAB, we have delta H mixing value and delta B mixing value. In this case, delta H mixing value must be, less than 0. Delta H mixing value must be less than 0. We have another condition along with this is delta H must be less than 0. Delta H must be less than 0, and it is the same here is the delta B is also delta B also less than 0. Delta H must be less than 0 and delta B also less than 0. If it is less than 0, it means it has negative value. Delta B also has negative value and delta H also has negative value. Okay, understood. Now, what is the meaning of negative value? Because of weak A and the BB bond. Okay, because the weak A and the weak BB bond, these bonds breaks down easily. These bonds, the bond between the two solid particles and the bond between the two solvent particles breaks down easily, and a new bond is formed between the solute and the solvent particles between A and B, and in this bond formation, higher amount of energy is releasing out. That's why it has delta H negative value. Okay, that's why it has delta H negative value, and volume also decreases. That's why it has the delta B mixing negative value. Understood? Next, what we have, what are the examples which undergo negative deviations? The examples are HNO3 and water. HNO3 and water. Second one is chloroform and acetone. Third one is acetic acid and pyridine. And fourth one is the hydrochloric acid and water. Understood? Okay. Now, our next topic is azeotropic solutions. What is our next topic? Our next topic is azeotropic solutions. What are azeotropic solutions? Azeotropic solutions are those solutions which have same composition in its liquid form as well as in its vapor form. Okay, what are the azeotropic solutions? Azeotropic solutions are those solutions which have same composition in its liquid form as well as in its solid vapor phase. Okay, understood? Next, there are how many types of azeotropic mixtures? The type of azeotropic mixtures are minimum boiling azeotrope. First one is minimum boiling azeotrope and second one is the maximum boiling azeotrope. First one is the minimum boiling azeotrope and second is the maximum boiling azeotrope. What is minimum boiling azeotrope and what is maximum boiling azeotrope? Let us define both the terms. Minimum boiling azeotropes has the boiling point less than both the components. Okay, minimum boiling azeotropes are those solutions which have less boiling point than both the components. Okay, And maximum boiling agent drops are those type of solutions which have greater boiling point or a higher boiling point than both the components present in the solution. Either of the components present in the solution. This is the basic difference between the minimum boiling agent drop and maximum boiling agent drop. What are the examples? What are the examples of minimum boiling azeotrope? The example of minimum boiling azeotrope are noted down. We have a mixture of 94.5% ethyl alcohol and 4.5% water by volume. 4.5% water by volume. Second example, we have the second solution, maximum boiling azeotrope. We have, what is maximum boiling azeotrope? In the case of the maximum boiling azeotrope, the solution must have the higher boiling point than either of the component, than either of the solute and the solvent. Understood? For example, we have a mixture of 68% HNO3 and 32% H2O by mass. What is the example? 68% HNO3 and 32% H2O by mass. What is the meaning of this type of example? It's 68% HNO3 and 32% water by mass. It means we take these compounds by just measuring its mass. If we are going to make a solution, it means we take 68 gram. If we are going to make the 100 gram of the solution, we are just taking 68 gram of HNO3 and 32 gram of water. Okay, this is the percentage level and it may be called as the solution by mass. Okay, understood? These are taking it grams. Now, what we have, our understood both the topics. First topic is the negative deviation from the ideal behavior and second topic is the azeotropic mixture. Second topic is the azeotropic mixture. What are azeotropic? I am just revising what I have taught. What are azeotropic solutions? The binary solutions. Binary solution means the solution which have solute and the solvent particles. The binary solution, it means it has only the two components, not more than that. So it has one solute component and one solvent component. Okay. So these are the two types of the azeotropic solutions: minimum boiling azeotrope and the maximum boiling azeotrope. Minimum boiling azeotrope has the boiling point less than either of the component, and maximum boiling azeotrope has the boiling point more than either of the component. Okay, understood? These are the azeotropic mixture solution. These are the azeotropic solutions. Next, we have our next topic is the colligative properties. Okay, colligative properties. Our next topic is colligative properties. Those properties which depend on the number of solute particles. Those properties which depends on the number of solute particles, molecules, atoms or ions, but not upon the nature. Those properties which depends on the number of solute particles but does not depend upon the nature are known as the colligative properties. Okay, it depends on the number of particles, not on the nature of the particles. Those properties are known as the colligative properties. Can you give me the example of the colligative properties? We have so many examples of the colligative properties here. The properties depend on the number of moles, not the nature of the compound or the nature of the component. What is relative lowering of vapor pressure? Okay, first is relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure of the solution. These all the four examples are totally new for you kids. Okay, all the four examples are totally new for all the kids. We discussed all the four examples one by one in the coming classes. What is just I am giving some summary. elevation in boiling point or depression in freezing point. By just name, by just listening the name elevation in boiling point, it means there is increase in boiling point. Depression in freezing point, it means there is decrease in boiling point. Okay, these are the properties which depend upon the number of moles of the particles or the component present in the solution. That's why these are known as the colligative properties. What are, again I am saying, what are colligative properties? Colligative properties are those properties which depend upon the number of moles of the particles but does not depend on the nature of the particles which it has. Okay, understood? Examples are the relative lowering of vapor pressure, elevation in boiling point, depression in freezing point. These are the examples. We all discuss all the 4 examples in the coming classes. Okay, thank you.